Now what we're going to look at is, in front of you I've set up a spring, and I've set up, we have a 0.5 kilogram mass. I'm going to put it on here. Now, one of the things that I'm not going to go through today is the fact that when you have a vertical mass spring system like this, you can basically ignore the gravitational potential energy and set the new zero line at the location where it is at rest when it is vertical like this. There's a whole derivation of that in your book, but I'm not going to take the time to go through that. Again, so all we have to look at here is the kinetic energy and the elastic potential energy. So what I'm going to do is I'm going to take and I'm going to offset it slightly so that what we have here is an object in simple harmonic motion. We have position as a function of time. I click start, and we graph the position as a function of time. And you can see this graph. As we were talking about, we talked about the sine and cosine, right? You could literally see that in our picture here. So let's zoom in a little bit. Actually, let's do this first. We're going to click and drag velocity in and click and drag acceleration in. So we have position, velocity, and acceleration as a function of time. We'll zoom in, and we will just get, we'll go here, zoom in, this portion here. So what you're looking at here is the velocity, position, velocity, and acceleration. Position was cosine. Velocity was negative sine. And acceleration was negative cosine. Right? There they are. You can see them. I want to walk through, we're actually going to figure out some stuff about this particular demo. We have the mass of the object. Do I have to stop it so that you stop staring at it?
No, it's okay.
That's not a good sign. I'll give you another minute. All right, the mass of the object is 0.5 kilograms, 0.5 kilogram. Let's just look at the position as a function of time, because that's really what we're going to use here. We have the position as a function of time. Now, we could figure out the time for one full cycle. That would be from here to here. If we go and look at a table, we can see the position as a function of time. We have here all of these times. The initial time is 1.9820. And the final time there is 2.8820. In other words, the period is going to be equal to the time final minus the time initial, or 2.8820 minus 1.9820. What is the period of this mass spring system? 0.9. Say again? 0.9. We could probably go with 3 sig figs here. 0.900 seconds is the period of this mass spring system. We can also figure out the amplitude. We'll go back to our graph here. In our graph, now we need to figure out the amplitude. So we're just going to look at now half of the whole cycle here. We'll come back to the table, just look at the position. And our initial position here is 0.589 meters. And our position final is equal to 0.701 meters. How do we figure out our amplitude from those two numbers? Going back to our graph. How do we figure out our amplitude? So,
it's the change in distance over 2.
Because when we take the change in distance, that's going to be all the way from here to here. But the amplitude, as Potterella was pointing out, is the maximum displacement from the equilibrium position, or the height of a crest, which in this particular case is going to be 0.701 minus 0.589 divided by 2.
0.056.
0.056 meters. So we now have the amplitude of this motion. Okay. We can now figure out the period. Oh, actually, we can use the period now to figure out the spring constant. The period equals 2 pi times the square root of m over k. We have the mass of the object. We have the period. We can solve for the spring constant. Let's see. If we're going to solve for the spring constant, we get the period divided by 2 pi equals the square root of m over k. Period squared over 4, pi squared equals mass over k. K is equal to 4 pi squared times m divided by a period squared. Spring constant equals 4 pi squared times 0.5 divided by 0.9. Yeah.
Should be 0.9 squared.
Thank you. 0.9 squared. Thank you. Spring constant.
Is that 0.56?
0.5.
Yeah. 2.4369.
We'll just go with 3 sig figs here. 2.44. Rohan, what are the dimensions of the spring constant? Good. We have figured out the spring constant. Okay. We also can figure out the angular frequency. What was the equation for the angular frequency in a mass spring system? Travis?
Square root of K over M.
K over M. Note that's actually the same thing as change in theta over change in time, or 2 pi divided by the period. So at this point, we could actually take the square root of the spring constant divided by the mass, or 2 pi divided by the period. We have both. So we'll do 2 pi divided by the period, which is 0.9. The angular frequency of, bless you, this object in simple harmonic motion. 6.981. Great. What are the dimensions on the angular frequency? Stacey. Two pi what?
Divided by 2 squared.
Sorry, we'll work it out. 2 pi what? What was this?
Radians.
Divided by
Seconds.
radians per second. We have the angular frequency. Angular has the exact same dimensions as angular velocity, radians per second. Okay, we now can figure out the position as a function of time. It's equal to A times the cosine of omega t plus phi. We have the amplitude. 0.056 cosine of, we have the angular frequency, 6.98 times t now, plus phi. Okay. If I started with the mass at the amplitude above the equilibrium position, who could tell me what phi would be? Vasily. Actually not be negative pi over 2. Think of your cosine wave.
0.
What would phi be if I started with the object? So here's the equilibrium position, and I have the object located at the amplitude above the equilibrium position.
0.
Cosine, remember, looks like this. What would phi be? So, 0. Okay, what would phi be if instead I started it down here at the amplitude below the equilibrium position? What would phi be then?
Pi.
Pi. So notice that's how phi works in this particular case. It doesn't really matter where we start it, so we'll just set phi equal to 0. So we will just let phi equal to 0. So we now have the position as a function of time of this object in meters. We can also figure out the velocity of the object as a function of time. How are we going to figure out the velocity of the object as a function of time, Vlad?
We're going to take the derivative of
Go ahead, take the derivative of position as a function of time.
it's going to be 0.056 times 6.98 times negative sine of 6.98t.
So, can I please have 0.056 times 6.98?
Mr. Hall, I'm gonna answer that because wrong. It's
Which one?
for the K, I think it's 21.9.
We got the spring constant wrong?
I think so. Because I was doing square root.
That's 21 point.
Yeah, 21.932.
So 21.9 newtons per meter. The sad part is that there are 29 of you who should have noticed. That's insane. All right, we got the spring constant. So the velocity 0.056 times 6.98. Please again. Yeah, that's all I want.
0.39088.
Times the sine of 6.98t. In other words, we just figured out the velocity as a function of time is equal to negative 0.391 times the sine of 6.98t. That's, of course, in meters per second. We now know the maximum velocity of this mass here. Michael, what is it? The maximum velocity. What's the maximum velocity? Get their hand out of your mouth and talk to me. What's the maximum velocity? Meg, help them out.
0.3908.
Right here. So 0.391 meters per second. We can also figure out the acceleration as a function of time. How are we going to figure that out? Dorston. Go ahead.
Okay, so that would be,
We should take the derivative of this one before we wrap.
okay. So you would do, so negative 0.308
9088. Okay.
times
Great. Can I please have the 0.39088 multiplied by 6.98?
0.2728.
Can't be less.
2.72.
Thank you. 2.72.
Yeah, that's what I meant.
Fair enough. Cosine of 6.98t. So we now have the acceleration as a function of time. It's equal to negative 2.73 cosine of 6.98t. That's in meters per second squared. We also have the maximum acceleration. The maximum acceleration is what, Spencer?
2.73
Meters per second squared. So notice all the information we have about this object, just starting with the period, the amplitude, and the mass of the object. Jenkins.
Can you explain what phi is a little bit more?
Phi is simply the phase shift. So, for example, if you have cosine, it starts at the maximum location, right? negative cosine would start down here. So if you could, rather than using the cosine with a phase shift of pi, you could use negative cosine, right? Rather than using sine, or cosine with a phase shift of pi over 2, you could use negative sine, right? So it's just shifting where it starts, essentially. Matt?
Why is the maximum velocity? Why does it change from negative to positive?
Because the minimum velocity would be negative of this value, the maximum would simply be the positive. The velocity varies in value from the positive of this number to the negative of this number, back and forth. So if we're talking about the maximum, it's going to have to be the positive value.